this video, we will be defining the atomic weight or average atomic mass of an element. In the previous video, we discussed atomic symbols and atomic numbers. In this video, we will be discussing the average atomic mass of an element. In future videos, when we need to know the mass of an element, this is the value that we'll be using. The average atomic mass, or what's sometimes called the atomic weight, of an element is the weighted average mass of the naturally occurring isotopes of that element. To attain the average atomic mass, one takes the natural abundances of an isotope and multiplies that by the atomic mass. One then does this for all of the naturally occurring isotopes of that element. With that definition, let's do two problems concerning average atomic masses. In this first problem, we're given the masses and natural abundances of two different isotopes of potassium. The problem then asks us to calculate the atomic mass of potassium. So going through our problem-solving strategies, in step 1, what are we being asked to solve? We're being asked to solve for the atomic mass of potassium. In the second step, what information are we given? We're told that potassium-39 is 93.258% abundant with an atomic mass of 38.964 atomic mass units. Potassium-41 is 6.7302% abundant with an atomic mass of 40.962 AMUs. And we also know, by definition, that the atomic mass is the weighted average of the masses of all the isotopes. Going through and solving this, the formula for atomic mass is just atomic mass equals the sum of all the naturally occurring isotopes times the atomic mass. We have two isotopes, so we're going to apply that to the potassium-39 and potassium-41 isotopes. Going through and plugging in the information for potassium-39 and potassium-41, we arrive at an atomic mass for potassium of 39.094 AMU. Now we're going to go through and do step 5, where we use estimates to determine whether or not the answer we obtained is reasonable. We're going to take potassium-39 and round its atomic mass to 39 AMU and its natural abundance to 95%. We're going to take potassium-41, round its atomic mass to 41 AMU and its natural abundance to 5%. Going through and multiplying, we obtain 37 AMU and 2 AMU. Adding together, we get 39 AMU, which is close to the result we obtain of 39.094 AMU. In this problem, we're going to calculate the natural abundance and atomic mass of an isotope of boron, given the natural abundance and atomic mass of a different isotope of boron, and the average atomic mass of boron. Step 1, what are we being asked to solve for? We're going to go through and calculate the natural abundance and atomic mass of boron-11. Step 2, what information do we have to solve this problem? We're told that boron has an atomic mass of 10.81 AMU, that boron-10 is 19.9% abundant with an atomic mass of 10.013 AMU. The atomic mass, we know, is the weighted average of the masses of all isotopes. We also know that the total natural abundance of all isotopes has to equal exactly 100%. We are now going to develop a strategy for solving this problem. We know the formula for average atomic mass. Breaking this down, the average atomic mass for boron is going to be the natural abundance of boron-10 times the atomic mass of boron-10. We know both of these values, plus the natural abundance of boron-11 times the atomic mass of boron-11. These are unknown. The natural abundance of boron-11 will equal 100% minus the natural abundance of boron-10. Rearranging the above equation, solving for the atomic mass of boron-11, we have the atomic mass of boron-11 equaling the average atomic mass of boron minus the natural abundance of boron-10 times the atomic mass of boron-10, all divided by the natural abundance of boron-11. In step 4, we implement our strategy. The natural abundance of boron-11 is going to be equal to 0.1 minus 0.199, which equals 0.801, which is equal to 80.1%. The atomic mass of boron 11 is going to be equal to 10.81 AMU minus 0.199 times 10.013 AMU, all divided by 0.801. This equals 11.01 AMU. So we've determined the natural abundance of boron 11 is 80.1%, and the atomic mass of boron 11 is 11.01 AMU. We're now going to go through and use estimates to determine if this is a reasonable value. We're going to round the average atomic mass of boron to 11. We're going to round the natural abundance of boron 10 to 20%. We're going to round the atomic mass of boron 10 to 10. Using 20% as the natural abundance of boron 10, we obtain a natural abundance of about 80% for boron 11. This is reasonably close to what we've obtained. Now, using the rounded values for the natural abundances and atomic masses, we obtain an atomic mass for boron 11 of 11.3, which is similar to the value we obtained of 11.01. The key takeaways from this video are that there are multiple isotopes of various elements. The atomic mass reported on the periodic table for a given element is the average atomic mass for that element, and the average atomic mass is the weighted average of the atomic masses of all the naturally occurring isotopes of an element. The next video will introduce you to the periodic table.